Welcome, and thank you for joining this webinar, Advancing Quantum Communication, Role, Impact, and Technical Foundations of Quantum Technologies in 6G and Beyond, prepared by Alpert Research Team. Quantum communication is transitioning from academic theory to strategic infrastructure. This webinar explains how physics, not math, can guarantee trust, and how quantum systems integrate realistically into modern communication networks.
When we try to scale QKD globally, we run into its single biggest constraint, the distance barrier.
Right. Classical fiber networks can cross oceans because they use cheap, plentiful optical amplifiers to boost the signal every 100 kilometers or so.
But the very law that makes QKD secure, the no cloning theorem, is also its biggest enemy here.
It's the ultimate double-edged sword. No cloning means you absolutely cannot make a perfect copy of an unknown quantum state. And if you can't copy it, you can't amplify it.
So the signal just gets weaker and weaker as photons are lost in the fiber.
And eventually it fades into the noise. In standard fiber, the maximum range for QKD is typically somewhere between 100 and maybe 300 kilometers. That's fine for a city, but it's useless for connecting, say, New York to London.
So how do we get around this fundamental physics problem? This brings us to what's often called the third generation of quantum communication.
The quantum repeater. A quantum repeater overcomes the distance limit by breaking a long channel into many shorter, manageable segments.
And then it stitches them together somehow.
The key is to generate local entanglement within each short segment. Then you use a clever quantum operation called entanglement swapping to link the entanglement from adjacent segments.
So you're not sending the original qubit all the way. You're sort of teleporting the entanglement, the correlation, across the entire distance.
You end up distributing entanglement between the two distant end nodes, Alice and Bob, without ever having to send a single fragile qubit over the whole lossy channel.
But I keep hearing that practical quantum repeaters are still decades away. What's so hard about building one?
Well, they require technologies that are still in their infancy. First, you need high-fidelity, long-duration quantum memory. You need to be able to catch and hold a quantum state reliably. Second, you need very robust quantum error correction to protect the states during the swapping process. And third, you need high-speed, reliable sources of entanglement. Until we really solve quantum memory and error correction, QKD is stuck on the ground or has to go through space. Satellite communication bypasses the need for all those difficult and error-prone quantum repeaters on the ground.
Satellite systems can support large-scale continental links, potentially up to 6,000 kilometers, without needing a chain of intermediate repeaters. Satellite QKD seems essential.
It's the only way right now, without repeaters. The Chinese Machias satellite demonstrating QKD over thousands of kilometers. Now the goal is intercontinental links.
And the technology is getting smaller.
Yes. People are now exploring CubeSats and small satellite constellations for QKD, which would make it cheaper and allow for dense LEO networks. You can then integrate these satellite links with terrestrial fiber networks at ground stations to create a global hybrid system.
When you move from fiber to free space, the challenges change. What are the specific hurdles of beaming single photons from space down to the ground?
The channel changes completely, yeah. Now you have to deal with atmospheric turbulence, which causes scattering, you have diffraction losses, and intense background solar noise that can just swamp a single photon detector. Overcoming this requires sophisticated engineering.
Well, research centers are actively working on this. They're using highly sophisticated technologies like adaptive optics. They use deformable mirrors to actively compensate for atmospheric distortions in real time. This ensures that the delicate single photon signal arrives at the ground station with maximum integrity. Are there other media being explored for these quantum channels?
Yes, the landscape is definitely diversifying for specific applications. Free space optical FSO links, outside of the satellite context, are already used for QKD between buildings or across urban areas. And high security research is exploring underwater communication using QKD-based optical or even acoustic signals for secure subsea links, for instance, between submarines or remote ocean sensors.
And what about scaling and reliability in dense networks? The sources point out that bulky, complex, discrete optical systems can pose problems.
They struggle with maintaining mechanical and thermal stability in a large-scale network environment. That makes them unreliable and expensive to interconnect. So the strategic direction is toward chip-scale QC systems, integrating all the necessary optical structures, modulators, sources, detectors onto silicon chips offers immense advantages in reliability, stability, mass production, and reduced interconnect cost. And that's essential for massive 6G deployments. The message is crystal clear. The integration of quantum systems into our network architecture is happening now, not in some distant theoretical future. We've established that quantum communication will not replace classical wireless networks, but it will redefine how trust, security, and optimization are built into 5G advanced and 6G systems.
Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.